Okay, hello, welcome back. This is Discrete Math 9.3. We're working with probability and do some counting stuff, and in particular counting elements in disjoint sets. And we have the addition rule as the first rule we encounter. Okay, so in particular then, if you can write your kind of universe or your sample space as a union of disjoint subsets. Okay, so they're disjoint, so I have to make a statement like a sub I intersect a sub j is empty when I is not equal to j. Okay, so if that's the case, then you can figure out the number of things in A. So I know I've been using the pound symbol for this, but I think I'm supposed to be using the N symbol, so I apologize. The number of things in A is going to be the sum of the number of things in these disjoint subsets. Okay, so let's look at a problem. Number one, they're asking how many different ways can you have strings, binary strings from 1 to 4 digits long. Okay, so binary strings again, like 101, 111, things like that. Just a list of elements of zero where they're all zeros and ones. Okay, so part A, how many binary strings from 1 to 4 digits long. Okay. And you could list some of them if you're not sure what the heck they're talking about. I'll try to. So 1 digit long strings would be like 0 and 1. There's only 2 of them. And then 2 digit long strings, well, there's 1, 0, 1, 1, 0, 0, 0, 1. So there's 4 of those. And then 3 digit strings, 1, 1, 1, 1, 0, 1, etc. Right? And then we need also the 4 digit strings, 1, 1, 1, 1, 1, 0, 1, 1, etc. Okay. Okay. So a way you can do this is just to count up all of them. You just count up the one digit binary numbers, then count up the 2 digit binary numbers because they're all disjoint sets, right? There's none of these guys is also in this set down here. So to count them all, you just count up the disjoint subsets. So the number of things here in this first set, well, you kind of think of it in the slot method, there's 2 of them, right? And then the number of things here, in the first choice there's 2 possibilities, and then you have 2 more possibilities, so there's 4 there. And then here there's 8, 2 cubed. And then here, how many of those are there? There's 2 to the 4th of them, so 16. And then the total, you just add those together, right? You add 2 plus 4 plus 8 plus 16, and 10, 0 added 2, so 30 of them altogether. Okay. Okay. Let's see, part B. How many strings are from 5 to 8 digits long? Okay. How many binary strings again? From 5 to 8. Okay. And now it's a little easier, right? Because we kind of see how the pattern's going to work. So it'll be 2 to the 5th plus 2 to the 6th plus 2 to the 7th plus 2 to the 8th. Okay. It's almost like it's one of these geometric sums that we have formulas for. So if it gets out of hand, you can use a geometric formula to quickly evaluate the sum. Anyways, the next topic, difference rule. So if you're given a set that's a subset of another set, so for example, I'll draw the Venn diagram even though I'm opposed to Venn diagrams. Let's say I have some set B, which is inside this other set A. Okay? So we'll say if B is a subset of A, then we could say the number of things in B plus the number of things in A minus B, which is this kind of donut region here on the outside of B. So plus the number of things in A minus B should equal all of A, right? So it equals the number of things in A. Okay. So this gives us a nice clever formula for figuring out the number of things in A minus B. Presuming that B is contained in A, that will just be the number of things in A minus the number of things in B. Okay, and we'll use this in some of the exercises. So in particular then, let's take a look at number 3. And we're trying to find the number of integers from 1 to 999 with no repeated digits. Okay, so this is part A. First issue at hand, find the number of integers from 1 to 999 with no repeated digit. Okay, so again we can split this up into 3 subsets, 3 disjoint subsets. We'll count up the number of integers with 1 digit, the number of integers with 2 digits, and the number of integers with 3 digits. In each case we have no repeated digit. So the number of integers with 1 digit, there are, and we don't include 0, right, because we're going from 1 to 999. So there are 9 of them, 1, 2, 3, 4, 5, 6, 7, 8, 9. In the second case, we have 9 choices for the first number. And then because we have no repeated digits, we have then 9 for the second. If we were allowed repeats, we could say 10 for the second, right? We could say 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. But one of them is going to be used in that first digit. So we'll have to say just 9 times 9. Okay, so that would equal 9 times 9. I accidentally got it. And then lastly, there's 9 possibles for the first digit. Okay, you can't have 0 there if that's not obvious. Hopefully that will. Okay, and then the second digit, you used 1 in the first digit, so you can't repeat that. But now you have 0 kind of thrown back in. Okay, which is why it seems like I've not gotten rid of any, but I did. Okay, so this, and both the 2-digit numbers and the 3-digit numbers, the first digit is restricted to only 9 possibilities because you can't use 0 in the first digit. Okay, if that's not clear, hopefully that is now. Okay, so anyways, we get back to 3-digit numbers. The first digit, there's 9 possibilities, 1, 2, 3, 4, 5, 6, 7, 8, 9. But in the second digit, there's only 9 possibilities because you can't repeat the number you use first. But then there's another one in there because now you can use 0 where you couldn't use 0 before. Okay, and then the last slot, now we're down to 8 possible numbers. So we have 9 times 9 times 8. Okay, so using our addition rule, 9 plus 9 times 9 plus 9 times 9 times 8 would be the total number of integers from 1 to 999 with no repeated digits. Okay, part B is in line with this previous idea at the top of the screen, the difference rule. Okay, in particular, we want to figure out the number of integers that have at least 1 repeated digit in the same range. So ends from 1 to 999 with at least 1 repeated digit. Okay, so how do we figure this out? Well, it's going to be the difference between the total number of integers between 1 and 999 and this other set, the integers that have no repeated digits. Okay, and we call this first thing here, this set A, and this set B, and in that case, this original set that we're after would be A minus B. It's just the set of all numbers, and we know both of these values, right? The set of all integers from 1 to 999 is just 999 minus 1 plus 1, which is 999. The second set, integers with no repeated digits, is just the set from part A. Okay, so we also know that that one is 9 plus 9 times 9 plus 9 times 9 times 8. Okay, so using the addition rule, now we can kind of figure out that number, and it will be 999 minus 9 plus 9 times 9 plus 9 times 9 times 8. Okay. Then they're going to want to throw in some probabilities. So here they want to know the probability of picking one number from 1 to 999 such that at least one of the digits is repeated. Okay, so that's just going to be this value above in part B, divided by the total number of integers. Okay, so it'd be 999 minus 9 plus 9 times 9 plus 9 times 9 times 8, all over the total number of possible integers, 999. One thing to note here is you could rewrite this, right? So the method to my madness, why didn't I just multiply those out? We can rewrite this as the difference of two fractions. Okay, so the first fraction, 999 all over 999, minus this 9 plus 9 times 9 plus 9 times 9 times 8 all over 999. Okay, so the first fraction is just 1, right? And then the other guy, what the heck is that thing? That's just the probability of getting an integer that has no repeats. Okay, probability of picking an integer with no repeats. And this brings us to our next formula. Basically, if you want to know the probability of an event, you just take 1 minus the probability of its complement. Okay. So in general, then we have this sort of new law, section 3 in my notes, the probability of a complement. Okay, so the probability of something not happening is equal to 1 minus the probability of that something happening. Okay, and we'll look at some of these problems later in the homework. Okay, so I'll go on WebAssign here in a bit. One side thingamajig are these anagrams. I always have to include these. It's part of our objectives, so maybe not totally aligned with what we're doing right now, but just very quickly, how many different ways can you rewrite the word quick? I think we had this kind of problem in the last section, right? So basically 1, 2, 3, 4, 5 letters. In the first place, there's 5 choices, and then 4, and then 3. Okay, it's 5 factorial. How many ways can you arrange the letters of the word quick if you keep the letters Q and U together? Okay. So what you do is just kind of pretend that Q and U is one tile all to itself, or one letter. Okay, so you really have 1, 2, 3, 4 letters you're ordering. So you're going to end up 1, 2, 3, 4. So 4 times 3 times 2 times 1 is 4 factorial. Part C, they want to know how many different ways can you do this if you're using QU or UQ. Okay. So this is one of those disjoint addition rule type problems. Basically, all the different words you can form where QU is together, that's going to be 4 factorial. And then the number of different words you could form with UQ, that's going to be 4 factorial. These are disjoint sets, so you can add them together to get the total number. And of course, that's just 2 times 4 factorial. Okay. Next is the inclusion-exclusion rule. So section 4, inclusion, exclusion. And what we're trying to do is figure out the number of things in a union. Okay, so the problem with figuring out the number of things in a union, if the sets are not disjoint, is that you may overcount. Okay, so before, if these A and B were disjoint, in other words, there was nothing here, all you had to do is figure out the number of things in A and add it to the number of things in B. Okay, the problem in this section is that now it's may or may not be disjoint. So the number of things in A unioned with B, there's a problem of overcounting, right? So if you count up the number of things in A, you're counting up all this junk. Okay, so that's N of A. And then if you add it to the number of things in B, what's happening? There's this overlapping region, right? So number of things in B is all this stuff. Went a little bit outside the circle there. And what's happened is you counted the intersection twice. So you need to subtract away a little bit. You need to say, okay, we subtract away the number of things in A intersect B. Okay. And truthfully, if A intersect B is empty, then you don't have to worry about that last term anyways, right? So you just have 0 there, and you would have the formula from the original part of the book, of the chapter. Right, you just add up the different sets because they're all disjoint, and you don't have to worry about the last part. Okay, this extends to 3 sets, and you can have rules for more and more of them. Okay, so the sort of way this works is kind of weird, but we'll kind of go through it. Okay, so I'm trying to figure out the number of things in A union B union C. Okay. So A, and then B, and then C. Okay. So if I count the number of things in A, I will have counted this part, this part, this part, and this part once. Okay. And then if you count the number of things in B, you will have counted this part, this part, this part, this part once. And you see there's a problem. We've overcounted some stuff. Okay. And then if you count the number of things in C, you'll have counted this part, this part, this part, and this part. Okay, so what you need to do is first subtract away the number of things in A intersect B, okay, and then that'll get rid of one thing in each part, right? So it'll get rid of one of these guys. Let me get my eraser. Got one of those, and I'll get rid of one of those, right? Okay, and then I'll subtract away the number of things. Hopefully you're looking at the Venn diagram. I sort of got rid of some dots there. The number of things, I subtract away the number of things in A intersect C. Okay, so again, look at the Venn diagram. I'm going to erase the things that I overcounted here. And I erase one thing, right? I erase one thing from A intersect C in both little regions. Okay, so I get rid of one of these guys here and one of these guys here. Okay, and then I'm going to subtract away the number of things in B intersect C. Okay. And again, that'll allow me to subtract, if you look at the Venn diagram, one of the things here and one of the things here. Okay, so what's the problem? The problem is now I've subtracted too much. Okay, so before I added in too much and I subtracted to get rid of the extra stuff. Now in this process I've subtracted too much and I'm missing that middle part. Okay, so what you do is then add back in the number of things in A intersect B intersect C, and that'll count. If you look back at the Venn diagram, then that'll put one thing back here in the middle. Okay, and we have counted everything just once. Okay, so let's take a look at one of these types of problems. This is 23. how many integers from 1 to 1,000 are multiples of 4 or 7. So we're dealing with integers from 1 to 1,000, and we want to know the number that are in the set A, which is the set of multiples of 4, and the number of things in set B is the multiples of 7, right? Okay, so in order to figure out the number of things from 1 to 1,000 that are multiples of 4 or multiples of 7, I'm going to have to figure out what? I'm going to have to figure out the number of things in A, add that to the number of things in B, and then subtract away the number of things that are in both. Okay, so here we go. The number of things in A. So we're looking at multiples of 4. So you can do one of these listing things: 1, 2, 3, 4, 5, 6, 7, 8, 998, 999, 1,000, and kind of enumerate all the ones that are multiples of 4. So here's the first one, 4 times 1, or 1 times 4 if you'd rather. Here's the second one, 2 times 4. And then here's the 25th, right, or 250th. So there must be 1, 2, 3, 4, 5, 6, 7, 8, 9, all the way up to 250 of them. Okay. So you could use your formula 250, the m minus n plus 1 formula, or n minus n plus 1. It'd be 250 minus 1 plus 1, which is just 250. Okay, then we need the number of things in B. These are multiples then of 7. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, so the first one here, 1 times 7, and then here's 2 times 7, blah, blah, blah. This guy is 142 times 7. Okay, so there's 1, 2, 3, 4, 5, 6, 7, all the way up to 142 of them. Okay. Then we need the number of things that are in both. The number of things that are both multiples of 4 and multiples of 7. So how do I figure out those? Those are the guys that are multiples of 28, right? So multiples of 28, so 4 times 7, right? Okay, so that's 1, 2, blah, 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 all the way up to 28. And then the next one would be 56. And then keep on going. I've already figured it out, so that's why I'm kind of blowing through it. But the last one will be 980, which you can find just by dividing 1,000 by 28, and then taking the floor of that number and then multiplying that number, that result, by 28. You should get 980. Okay, but anyways, this is 1 times 28. This is 2 times 28, all the way up to 35 times 28. So there's 1, 2, 3, 4, 5, 6, 7, 8, all the way up to 35 of them. Okay, so we got all the numbers that we need. Now all we have to do is plop it into this formula here that I put the arrow at. So it would be the number of things in A union B is the number of things in A, which is 250, minus the number of things in B, which was 142, minus the number of things in the intersection, which is 35, which means there's 357 integers that are multiples of 4 or 7. Okay, so then they'll ask some probability questions. What's the probability that your randomly selected number is a multiple of 4 or 7? Okay, and that'll just be 357 divided by the number of integers from 1 to 1,000 inclusive, which is 1,000. Okay. Then thirdly, the number of integers that are neither multiples of 4 nor multiples of 7, which is just the complement, right? So you take the number of things in the total universe that we're dealing with, which is the total number of integers, which is 1,000, and then subtract away the number of things in A union B, which we just found to be 357. Okay, so you get 1,000 minus 357, which is your answer, whatever that is. Okay, you get your calculator out. Okay, the last thing we'll look at are these birthday problems. There's one in the homework like this. I'll do the version where instead of, so they want you to be surprised by the fact that you only need probably like, I don't know, 20 some people before somebody is going to have a birthday that's the same as somebody else. Okay, our problem, instead of looking at that problem, I'll look at finding the probability that two people have the same birthday month. Okay, so the first question, they kind of walk you through it. So the first question is, how many different ways can 4 people have birthday months? Okay, so 1, 2, 3, 4, and examples like June, July, September, maybe September, January, June, August, all of those different strings. So in the first case, there's 12 possibles, and then there's also 12 and 12 again and 12 again. So the total number of ways people can have birthdays given 4 people is 12 to the 4th. Okay. Then the total number of ways that people can have birthdays, if none of them are allowed to have the same birthday, well, that's just going to be what? Well, in the first pick, there's 12 possible, and then there's 11, and then there's 10, and then there's 9. Okay, and if you remember your pick notation, it's just 12 pick 4. Okay. Then they want to know how many people, how many ways are there for people in a group of 4 to have such that at least 2 people have the same birthday. Okay. If you think about these sets, this is the set of people where for any birthday combinations. So this is the number of things for any birth month combination. The second set was the number of possible ways that no one has the same birthday or birth month. And then we want to know the number of ways that at least 2 people have the same birth month. Okay, so this is just a difference problem. You're taking the number of ways, anyway, for people to have birthday month combinations, which we just found was 12 to the 4th, and then subtracting away the number of ways that no one has the same birthday month in a group of 4. So that would be P 12, 4. Okay, and then part D, what's the probability that in a group of 4, at least 2 of them will have the same birth month? Well, you just take the answer from part C and divide it by the total number of birth month combinations. Okay, so that'd be 12 to the 4th. And if you evaluate that in your calculator, you're going to get a pretty high percentage, right? You would expect 2 people, at least 2 people, have the same birth month in a group of 4. Okay, and then they go on, and the question is, how many people do we need before over 50% chance of having 2 people with the same birth month? And what you're going to do is kind of just trial and error. So we kind of have the formula that we're using, and you're going to go 12 and just put in numbers for n, right? So P of 12 comma n all over 12 to the n. Okay, and you'll keep trying the n values until you get something over 50%, and it turns out 5 will work. Okay, so when n equals 5, we'll get 12 to the 5th minus 12 pick 5 all over 12 to the 5th, which will be about 62%. Okay. Okay, for the birthday problem, then it's just a matter of replacing 12 with 365, right? And then you keep going through the process. At the end, it'll be something like 365 to the n minus 365 pick n all over 12 to the n, and you just plug in values for n until you get over 50%. I think it's probably like 23. Okay, you need about 23 people. So in my classrooms when I teach, it's always fairly likely that 2 people will have, I mean, it's over 50% probability that 2 people will have the same birthday. Okay, let's take a look at maybe some homework problems from online. So I was a good student and I did all my homework already. Let's see what we got. Okay. So these are just some. Okay, this one, let's try this guy. So at a certain company, passwords must be from 4 to 6 symbols long, composed of 26 letters, 10 digits, and the 14 symbols. How many passwords are possible if repetition of symbols is allowed? Okay, so how many symbols and complete do we have? So there's 26 letters, then there's the 10 digits, and then the 14 symbols. Okay, so 6 plus 4 is 10, carry the 1, 1, 2, 3, 4, there's 5, 50. Okay. We want passwords from 4 to 6 symbols long. So this is that disjoint rule for adding up the subsets. So we have 4-digit long passwords, 5-digit long passwords, and then 6-digit long. Okay. So if you're allowed to repeat, then it's going to be this huge number of them. So we have 50 to the 4th plus 50 to the 5th plus 50 to the 6th. Okay, whatever the heck that is. Usually I just go to my calculator on my and hope it can figure it out without having to go to scientific notation. Okay, so what do we have? 50 to the 4th plus 50 to the 5th plus 50 to the 6th is, yeah, some huge number. 1, 5, 9, 4, 3, 7, 5, 0, 1, 2, 3. Okay, let's see if that's it. Yeah. How many passwords contain no repeated symbols? Okay, so this is kind of the same thing, except for each letter we've used one. So the first choice we have 50, and then we have 49, and then 48, then 47. Okay, so basically that first one is 50 pick 4, and then plus 50 pick 5, and then plus 50 pick 6. Okay. I don't think the calculator will do that. You'll have to do it kind of by hand. Okay, so 50 times 49 times 48 times 47 plus 50 times 49 times 48 times 47 times 46 plus 50 times 49 times 48 times 47 times 46 times 45. Okay, and some other huge number. That's right. How many passwords have at least one repeated symbol? So now you're doing a difference, right? You're taking the total number of passwords, which was that 50 to the what was it? 50 to the 4th plus 50 to the 5th plus 50 to the 6th. And then you're subtracting away all these passwords that have no repeats, right? So 50 pick 4 minus 50 pick 5 minus 50 pick 6. Okay, and that should be your answer for that. And then what's the probability that randomly chosen password has at least one repeated symbol? That's just going to be that number there that I just wrote out, divided by the total number of passwords, right? So divided by 50 to the 4th plus 50 to the 5th plus 50 to the 6th. Oh, some of these loopy ones are kind of weird, sort of algorithms type stuff. So now we have a loop where the inner one is kind of dependent on the outer one. So it's going for I equals 1 to 6, and then in the inner loop for j equals 1 to I. Okay, and then it's repeating all that. So for the first one, for the first loop when I is 1, j is going from 1 to 1. Okay, and then the second loop, I goes to 2, so j will have to go from 1 to 2. Okay, and then for I equals 3, j will have to go 1, 2, 3. And then when I goes to 4, j will have to go 1, 2, 3, 4, etc. Okay. So what's happening is we have to add all these up. So there's 1 of those, 2 of those, 3 of those, 4 of those. There'll be 5 for the 5th loop, and then 6 for the 6th loop. Okay. And you could literally write them all out if you wanted to, but at the end of the day, it's going to be just the sum of the first 6 numbers. So 10, 21. Okay. So in general, if you have a loop for I equals 1 to n, and then the inner loop is going from j equals 1 to I, the total number of executions on the inner loop is going to be n times n plus 1 all over 2. Okay. Let's see what else we got. This is number 11. 9 new employees, 2 of whom are married to each other, are to be assigned the 9 desks that are lined up in a row, and each assignment of the employees to desks is made randomly. If the assignment of employees to desks is made randomly, what's the probability that the married couple will have adjacent desks? So there's 9 new employees, and you want 2 of them to kind of be together. 1, 2, 3, 4, 5, 6, 7, 8, 9. So if they're together, I don't know, maybe they're right here and right here. So after you pick those 2, then the randomly selected rest, you can't repeat them because there's only, they're humans. So there's 7 left over. So 7 times 6 times 5 times 4 times 3 times 2 times 1. So they could be in that ordering, or they can be in this ordering, right? And then they could be in this ordering, and then this ordering. And you just sort of have to add up those disjoint sets, right? So there's they could be here and here, that's 1. They could be here, here, 2, 3, 4, 5, 6, 7, 8 possible places. And in each one of those 8 cases, there'll be 7 factorial possibilities for the seats of everybody else. So it's going to end up being 8 times 7 factorial. In other words, 8 factorial for that first answer. They want to know the probability. If it's random, what's the probability they'll be sitting next to each other like that? Well, that's just this 8 factorial, the number of ways they could be sitting next to each other, divided by the total possible number of ways they could be sitting next to each other, which will be seems like that should be 9 factorial. I think. So 1 divided by 9, 11%, that's not right. Oh, I see what I screwed up. So it could be like Jim and Betty, or Betty and Jim. So there's twice the number of these. Hold on. Yeah, I'm sorry. I forgot to, yeah. Okay, so one more time. Okay, so there's 9 people, 1, 2, 3, 4, 5, 6, 7, 8, 9, sitting in a row. We want to count out the number of ways that 2 people could sit together, like, and they're supposed to be married or something. So like Jim and Stephanie or something. Okay, so Jim and Stephanie. So they could sit there, but then on top of that, they could also do, that's what I forgot, they could also sit like that. And then the leftovers, how many people are left? There's like 7, 6, 5, 4, 3, 2, 1. Okay, and then, in the next sort of version of that, they could sit right here and here, or like this and this. Okay, and then the leftovers are 7, 6, 5, 4, 3, 2, 1. Okay, so there's 2 times 7 factorial ways here, 2 times 7 factorial ways here, and then you'll keep on going like that until they're sitting like this. And that'll be 2 times 7 factorial there. How many total are there? There was like sitting here, 1, 2, 3, 4, 5, 6, 7, 8, all the way up to these last 2 slots. So there's 8 of those, and you add them all up. There'll be 8 times 2 times 7 factorial, which is 2 times 8 factorial. The total number of positionings you could have is 9 factorial. So 2 times 8 factorial over 9 factorial, give me that about 22%. Okay, it's a probability that the married couple have non-adjacent. Well, that's the complement, right? So that would be 100 minus the 22.2, or the 77.8%. Okay. Let's see if there's anything else. This one's kind of weird. There's one proofy one where you have to do. We'll just leave it at that for now. Number 16 is kind of a puzzle type question. I think you can do that. Yeah, we'll leave it at that for now, and I'll see you next time. Okay.